let's take a look at a couple of standard ways in which we can implement or realize a transfer function. So we've worked a lot with our going from differential equation form to finding our transfer function, and also working with circuits to find our transfer function. We want to look now at actually going from a transfer function back to a standard representation of our signal, or of our system rather, and we'll work with a second order transfer function. So this is a second order transfer function in fairly general form. In any particular case, any of these b coefficients or a coefficients might be 0. Of course, one implementation would come directly from the differential equation. It's an implementation using differentiation systems. Unfortunately, although that works well in theory, it doesn't work well in practice. Differentiators amplify any high-frequency noise that may be present in the system, and that will tend to overwhelm any signal component that's present. So even though it's a nice, concise mathematical representation, as a practical implementation of our system using differentiators, we have some problems in practice. So the standard forms are all implementations of our transfer function in terms of integrators. These we'll look at what are known as the direct form 1 and direct form 2 implementation, and then we'll also look at some implementations involving op-amps, first order and second order systems, op-amp systems. The direct form 1 and direct form 2 forms are used quite frequently in control systems, so that you will see them again. They're also useful in MATLAB control systems toolkit. So how do we transform or convert our transfer function into one that involves integrators instead of differentiators? Recall, multiplying by s corresponds to differentiation, while dividing by s, or equivalently multiplying by 1 over s, corresponds to integration. So here for my second order system, I'll divide both the numerator and denominator by s squared. So that leaves me with b0 plus b1 times 1 over s plus b2 times 1 over s squared. And then in the denominator I'll have 1 plus a1 times 1 over s plus a2 times 1 over s squared. And then recalling the definition of our transfer function, it's equal to the Laplace transform of our output divided by the Laplace transform of our input. So now cross multiplying, I have b0, oops, let me write it with the y terms on the left would be the standard form. So I'll have 1 plus a1 1 over s plus a2 1 over s squared times y is equal to b0 plus b1 times 1 over s plus b2 1 over s squared times x. Or going back into the time domain, I'm going to have y here, inverse transform of 1 times y, and then I'll have plus a1 1 over s times y transforms back as the integral of y. Then I'll have a2 times the double integral of y. And then similarly on the right hand side, I'll have b0x plus b1 integral of x plus b2 times the double integral of x. And then I'm going to go to a new board here. Solving this for the output, I'm going to have y is equal to b0x plus b1 times the integral of x plus b2 times the double integral of x, and then minus a1 times the integral of y dt minus a2 times the double integral of y. So now I've got this in a form that I can go directly into a block diagram implementation of this equation and the corresponding system. So implementing this part first, I'll have x of t coming in, and we'll represent multiplication just by a little arrow, and then next to the arrow I'll put the coefficient I'm multiplying by. So on the right side of the arrow now I've got b0 of x. I also need to integrate x, so I'll do that with just a little integration block, and then that integral needs to be multiplied by b1. So this term now at this point would be b1 times the integral of x, and then finally I need a double integral, so I'll integrate the integral of x, and then that is multiplied by b2, and then the summation is usually represented like this. Just need two summers in this case. Positive signs here on each of the summers is assumed, and then so at this point I'll have b0, let me call this signal w of t. That's the underlying portion of the right hand side of this equation. It's b0x plus b1 times the integral of x plus b2 times the double integral of x. Now let's take a look at this portion of the right hand side. I've got y of t coming out of this. I'm going to need feedback now. In order to form y of t, it's this w of t signal minus all of these terms. So minus, I have to integrate y here, and then that gets actually multiplied by minus a1, and then do a second integral of y. That gets multiplied by minus a2. Then now I need to add these terms into w of t, so I can do that like this. And then w of t minus these terms actually gives me y of t, so I'll just tie that into my y of t here, and I've got a standard representation of a transfer function. This is known as the direct form 1 realization or implementation of the system. Another way to actually do this is to you can think about it in the block transform domain, or I'll work directly with h of s, but taking our previous expression for h of s and then factoring it like this, writing the numerator terms first. And we've got our denominator term. I can think of this as two separate systems with transfer functions h1 of s and h2 of s. Of course, we can swap the order of these two systems, so I can equivalently write h of s as h2 of s times h1 of s. Okay. Where h2 of s was on the previous board, it would be the blocks or the portion of the direct form 1 implementation that W1 feeds into. So and I don't swap, I still have the same input and output, but now I'm just writing down the blocks that make up the H2 system. That was my feedback system, where I had an integrator, minus A1, a second integrator, minus A2, and that came into this summer. And if you look back and compare this to the previous slide, you'll see that this was just a component of the system. I'm swapping the feedback component with the feed forward component, and so the other part looked like this: integrator, integrator, and then B0, B1, and B2. These come into 2 summers. The form, the output, Y of t. Now I am guaranteed that the output of this system would be the same as the previous system, but the signal in the middle here, I previously called that W of t. That would be something new here. This would not be the same as the W of t, the middle signal in the previous system. But I can notice something here. I've got parallel integrators. So, calling this signal Z of t, this would actually be the integral of Z of t. This would be the integral of Z of t. Similarly, at the bottom here, I'd have the double integral of Z of t and the double integral of Z of t. So I can actually, I don't really need 4 separate integrators. I can combine these and then actually write the system in a simpler form like this. Okay. So X of t coming into a summer, and then I've got these 2 integrators, and multiplying by minus A1 minus A1 and minus A2. Similarly, going in the feed forward portion of the system, I've got that integral of Z multiplied by B1 and B2, and then Z was multiplied by B0. Again, I've got my summers here. This is the direct form 2 implementation. This is also known as the canonical form, canonical representation of the system. Canonical is just another way of saying a standard form. So here this uses a minimum number of integrators, so it's become the standard representation of a second order system. And so you'll see that in MATLAB or Octave in the control systems toolbox, they've got several functions that can work directly with the direct form 2 implementation of the system, and then and a lot of those functions, they take as inputs the feedback coefficients A and the feed forward coefficients B. Let's take a look at 2 other representations that can be used in general. One is these are simple to implement using operational amplifier circuits. And so, for example, let's take a look at a specific example. Say I've got H of S is equal to 4S plus 28 over s squared plus 6s plus 5. The denominator here has real factors of s plus 1 and s plus 5, and then so I can factor one more time as 4s plus 28 over s plus 1 and times 1 over s plus 5. So one way, of course, then would be to represent this system as a cascade of two first-order systems. These first-order systems are known as bilinear forms, and we can there's a fairly straightforward implementation of a bilinear form in terms of an operational amplifier circuit. So one way to implement this system would be as a cascade of two first-order systems. It's called the cascade realization. We can get a parallel realization by actually just doing a partial fraction expansion on our transfer function. So using the same transfer function that I used in the previous example, which was, we already factored the denominator to s plus 1 times s plus 5. And partial fraction expansion here becomes 6 over s plus 1 minus 2 over s plus 5. And so again, I could view this as a sum of two transfer functions, and so I could realize this system using the parallel representation, H3 of s and H4 of s. And summing these together. So one way to actually implement this particular transfer function would be with two bilinear op-amp circuits, each implementing H3 of s, the other implementing H4 of s, and then coming into a summing amplifier. And then I would have a system that has the same transfer function as the original transfer function.